welcome back to the Wines channel. Today we have a presentation of a work that is actually the undergraduate thesis work of a student who has graduated recently, Johan Cholaku. Unfortunately, since he left, the presentation will be given by one of the senior guys, Ryan. So Ryan, please take it away.
Yeah, so hey everyone, I'm Ryan, and today we are going to talk about integrated communication and computing in millimeter wave channels. And let me just take a moment to also thank our collaborator, Takumi Takahashi from the University of Osaka, Nicholas Fruling, and of course, Giuseppe, Professor Abro. Yeah, so let's just jump right in here. So we have a short content list, some basic introduction and motivation as to why we are looking at this problem, the system model, the proposed receiver structure, and then a performance analysis. So jumping right into it, we have the context of this problem is that in 6G or even 6G plus 7G networks, we are supposed to have a lot of connectivity, a lot of high mobility, and of course, a lot of multifunctionality. So for example, the integration of techniques such as sensing and computing to our system. So the challenge here is that, of course, as you know, high mobility causes Doppler shifts, and of course, this breaks down the orthogonality of typical OFDM systems. And in the context of integrated communication and computing, these schemes often assume perfect CSI or static channels. And what we propose here is a framework for doing this operation, ICC, in time-varying millimeter wave channels. And the goal is to perform symbol detection, do over-the-air computing over the wireless channel, and track the channel, all of them simultaneously. And our main core contribution here is the use of a bilinear message passing algorithm for the JCD task, and of course another closed form combined expression for the computing task. So the system model is as follows. You have a bunch of UEs, MUEs to be clear, each of them transmitting a data symbol and a computing symbol. And you have a base station with NRX antennas. So this is a SIMO uplink scenario. And we assume that the channel is time varying and has high mobility. So this can typically be modeled via these clusters, as you can see with this sigma L of C. And we have M of these clusters as well to denote our millimeter wave channel. And the setup is, yeah, as I described before, we have the uplink SIMO system, and the goal of computing is to compute a function of these computing symbols, SM, for example, the arithmetic sum or arithmetic mean, geometric mean, so on and so forth. Can be any of them. And the communication goal is to, of course, decode each of the data symbols separately. And the challenge here is that, of course, due to these time-varying channels, we have our superposition that we need for the computing is distorted. So we have to take that into account when we design our joint estimation scheme. So under perfect synchronization between the users, the received signal is given by at a discrete time k, can be expressed as in equation 1, where this FRX is the receive beamformer and HM is the effective channel vector. So let me also note down one thing. So we can, of course, do a standard SVD as well for the receive beamforming or the transmit beamforming. And of course, since this is not a full MIMO system, we can use a quasi-orthogonal SVD as a beamforming technique to do this. So we can now describe what this channel looks like, or even before, what these transmit signals look like. So since we want to achieve two tasks, communication and computing, we can decompose our signals as dm of k and some psi m of our computing symbol. So this psi m denotes a pre-processing operation that you can do potentially. But here we just ignore it and set it as unity. But if you want it, it's there. You just have to reverse it at the receiver with the corresponding post-processing function. And we also assume that our data symbols come from a discrete constellation, for example, QPSK, and our computing symbols are real. Yeah, so now a target function is, for example, as an example given in equation 3, where you have a sum of S. So if you assume that these pre and post processing functions are identities, so you have just a sum on S, which is that's the arithmetic sum, right? So this is the function that we are looking at for now to simplify our system. And now we can go ahead and describe the time varying millimeter wave channel model. So this comes straight from the state of the art, where your time varying channel is a function of the paths, the clusters, the coefficients, of course, denoting how much power you have for each of the channel paths, and of course your ULA response vectors at the receiver. So this phi of Rx is the azimuth angle of arrival, and these clusters, these sigmas that we had before as well, represents the time varying small scale fading coefficient. So if we assume that this base station has a UPA, so a uniform plane array, we can write our functions, our response vectors as in equation 5 and 6. And given our time dependency, we can also model our scaling coefficients as in equation 7. So the proposed algorithm flow is like this. So for each time step, we have a prediction stage, we have an observation stage, and an update. And then finally, when all of this is done, we do have a computing stage at the end. So this is actually going to be a bit mathematically developed, because we have to develop a bilinear framework for doing the channel tracking and data detection. So just bear with me here. Some fundamentals first. We assume that the power allocation is done such that we have ED plus EC is equal to 1. And for now, since we want to have the computing functionality as an add-on to a communication system, we assume that the computing symbols have a fraction of the power of the communication symbols. So that's what is given here. And now we also assume that the soft replicas of the channel are defined with these definitions given here, with their respective mean squared errors also defined correspondingly with this size. So first we need to derive some second order statistics, assuming knowledge of a previous channel to do our channel tracking. And these are the variances that can be calculated with the closed forms in equation 8 here. And as you see here, for example, this theta here, bold theta, is actually the true channel variance at the first stage at time t equals 0. And I think there was also, yeah, this one is also the true variance at the first time step. So this is how you initialize the channel before you start tracking it. And what we can start with doing a channel prediction. So we consider discrete set of time indices determined by a window and with a parameter d and w. And your tau window can be defined as in equation 9 with the definition for tau max as given here. And at each window, the channel prediction is carried out to provide a better starting point for the estimates, because it's very important, because in message passing algorithms, in a message passing algorithm, typically these errors propagate. So you need to have a very good first estimate to start this procedure. So the channel prediction is quite simple. So given the channel at k is equal to 0, you can define the expectation like this. And to alleviate the effects, you can select a prior estimate k tau using equation 11. So this is not so tough to do, because it's a very discrete and very small space, and you can easily get the k tau which you need here. So this is the update step for the MSA channel estimate. Yeah, as you can see, it just follows the typical strategy that we use in Bayesian belief propagation, with some variances updated according to the previous estimates, right? So the first stage is the data detection framework. So after the channel prediction, we now have this step where we first initialize our data symbols to 0 as a first tentative estimate, and we have the mean squared errors set to the power of the data symbols, which is 1. And now we can treat the computed symbols as effective noise and write out our symbols, our received signals as in equation 13. And the first step that we can do is a soft interference cancellation, where we can remove the residual interference and noise from our received signal. And we can, of course, also calculate our covariance matrix for these soft interference cancelled symbols. And by writing out the probabilities, we can also extract an extrinsic mean and variance as in equation 17. And this eta k is the covariance matrix sandwiched by the channel matrices, channel vectors at those time slots and subcarrier. So after you have that, you can do a denoiser, which we can select to be the base optimal denoiser for QPSK, given by equation 18. And you can also update the variance as in equation 18b. And to make sure that you don't fall into some local optima, you can also do a damping for this algorithm, which is what's given in equation 19. So it's almost exactly the identical procedure for the channel estimation, except that you now want to estimate Gaussian quantities. So your factor nodes look like this. 21 is, for example, your self-interference cancellation, and then the PDFs of those symbols are calculated as in equation 22, with the variances given as in 23 and 24. And then you can do your belief generation, where you generate your extrinsic beliefs from these probabilities, and you have extrinsic mean and variance also as defined in equation 26. Same stage here, so I'm just going to skip the details. We just have a denoising and damping stage. And finally, we come to the computing aspect, where you have a target function you want to estimate, and you want to design the optimal MMSC combiner. So you can formulate an optimization problem that looks like this to minimize the mean squared error, and you can design a closed form combiner as given in equation 30. So all of these quantities have already been calculated in the belief propagation algorithm that we described before, so we can just use them as they are to calculate our closed form combiner. And the complexity of this is, of course, dominated by the matrix inversions for your covariance matrix, which is performed n times, and of course the window sizes that we use for the channel prediction stage. So for the total complexity, we have a quantity that looks like this. Of course, it's actually based, the dominating quantity is the number of subcarriers in the system. So for the over-there computing also, we need to calculate the closed form combiner. So we have a matrix inversion there as well, and we have a cubic complexity there as a result too. So I should actually note that there are ways to reduce this complexity. For example, instead of doing a belief propagation, a Gaussian belief propagation, we can uh, do a low complexity variation, such as approximate message passing as well. But of course, this will result in a lower performance for both the detection stages and the estimation stages. So for the simulation setup, we assume a typical carrier frequency of a millimeter wave system at 28 gigahertz with a bandwidth of 100 megahertz, 64 antennas at the base station, and the number of users are 4. And we use QPSK and 16 QAM, and we choose velocities of from 30 kilometers per hour to 120 kilometers per hour. So first, we can show some results for data detection. So as you can see here, the bit error rate is pretty good for almost all the cases. And as you see, when the velocity increases, the bit error rate, of course, degrades accordingly because of the OFDM structure that we use. And this blue line here is the gene-aided perfect CSI bound. And this is the computing performance. So as you also see here, the degradation does occur when the velocity increases, but it's not so bad in this case. And we now have two gene-aided bounds. For example, this black line here is when you have perfect data estimates, and this blue line is, of course, the previous perfect CSI bound that we had before. And finally, we also have some channel estimation performance where we have similar trends where your performance gradually decreases when you have a high velocity in the channel scatterers. But overall, the framework does work and converges properly. So in summary, we have a ICC system in time varying millimeter wave channels. We developed a low complexity bilinear message passing receiver, and we demonstrated also superior bit error rate and computing mean squared error. And of course, this does enable reliable edge computing, for example, in high mobility scenarios, which is expected in typical V2X scenarios or even drones, and removes the requirement of perfect CSI. So a future work is to do a wideband frequency selective analysis or also incorporate hardware impairments into the system. That's it, and thank you for your time. Any questions?
I have a question.
Thank you, Ryan. Yeah, go ahead.
Yeah.
In the beginning, when you described the system model and the transmit signal, you said that the data can come from a discrete alphabet like QPSK, and the computing symbols are real. Is
Yes.
this a limitation of this method, or why you cannot transmit complex? Is the extension trivial, or can you comment on that?
Yes. So good question. Yes, the extension is trivial. It's just assumed this way because I think at this point in time, the most recent state-of-the-art work was assuming that they were transmitting real symbols for the computing. So we just follow them and also transmit. But the extension to complex is trivial, and you can and nothing changes about the method because you can use the complex variation of the Gaussian estimator, the Gaussian denoiser, to do the estimation as it is.
If I may add to your response, Ryan, there has been work done by Eric showing that actually there is an inherent benefit in doing quadrature-based over-the-air computing. So it's actually better, even if you have a function to compute, to split into the INQ and do the two processes separately. Okay, so while, as suggested by Ryan, in principle, it is possible to extend, actually doing it on real only is not a limitation, but it's actually building on the results that we had before.
Yeah.
Anybody else? Any other questions or comments?
Yes, let me just pass on a question that we received at the conference. So one person asked, is it possible or does it make sense to replace the channel prediction by, for example, using a Kalman filter or not?
Yes, very good point. And I think actually there are some works that do this. I think I have double checked this, but yes, because this is a typical tracking kind of problem where Kalman filters are perfect. There have been uses of the of this. I think it's called a centered Kalman filter to do this channel prediction stage. But of course, at the cost of a bit of a higher complexity, right? So there's always this to take care of.
When you say higher complexity, in what sense?
I'm
Just
not sure. I'm not exactly 100% familiar with the Kalman filters, but I believe that there is some matrix inversion there as well.
yes, you are right. You have to compute the covariance and use it to
Exactly.
do the yeah. Mhm.
So that the covariance computation will lead to a cubic complexity here as well.
Yes, I agree. Okay, understand. Okay, anything else, guys? If not, I thank you very much, Ryan, for the presentation, and I see you guys next time in the wireless channel. Yes, anything else? Okay,
No, that's it.
then
See you.
thank you, guys. Bye.
Bye bye.